Welcome to the next session of Subject Engineering Maths, Chapter 2, Differential Equations. Now, in this session, we discuss some concepts, that is variation of parameters, followed by classroom workbook on Cauchy's linear differential equations, right? The next concept we have is variation of parameters. Let us see what is this. In last sessions, we have seen particular integrals of different cases. What is my equation? F of d into y equal to q of x. Now, we have seen particular integrals in several cases. One possible case is exponential function. Even in the second case also, it is exponential function. In case 3, it is sine function or cos. Even in case 4 also, either sine or cos. In case number 5, we have seen particular integral for the function e power ax into 5. In case 6, we have seen particular integral for polynomial expressions. Now, if I want to find the particular integral of some different trigonometric functions like tan or cot function, we know how to find particular integral for sine function. You know how to find particular integral for cos function. So, but my target is to get the particular integral of tan function. Even if I write tan x as sin x by cos x, there is no standard procedure to get the particular integral. By using sin by cos, you will not get easily particular integral of tan function. Therefore, in that case, we have variation of parameters. See, when you look at all the 6 cases, exponential function we have seen in 2 different cases. If a is not a root of auxiliary equation in case 1. If a is a root of auxiliary equation, we have seen in case 2. This is sine of ax plus b, cos of ax plus b, sine of ax plus b, cos of ax plus b. So here sine of ax plus b or cos of ax plus b, we have seen in case 3 when denominator is not equal to 0, when d square is replaced by minus a square, right? Let me write out this. See here in this case what we are doing is we are replacing d square by minus a square if the expression f of d is not equal to 0. But in this case, when you replace d square by minus a square, in that case f of d equal to 0. So therefore, we are replacing d square by minus a square in that situation. Here, when you replace d square by minus a square, if f of d is not equal to 0, we can replace this. In this case, f of a equal to 0. In this case, f of a is not equal to 0. And we have seen how to find particular integral in case number 5, e power ax into v, and for polynomial expressions. In case of polynomial expressions, we have gone through series expansions. Right. But my problem is, if I want to get the particular integral of a function other than this, how to handle this? Say for example, particularly tan function, cot, secant, cosecant, because we have seen only 2 functions, trigonometric functions, sine and cos. What about next 4 functions? We have secant, cos, tan, cosecant, etc., cot. So to get the particular integral of these functions, we have introduced a concept that is called variation of parameters. But the drawback of this concept is it is restricted to only second order equations. But in case of all the 6 different cases, you can handle any higher order equations, second order, third order, fourth order, right? Anyhow, somehow we can manage second order equations by finding particular integrals of tan, cot or cosecant, secant, right? Now let us consider second order linear equations with constant coefficients. Suppose I have an equation d square y by dx square plus p dy by dx plus qi equal to r. Here its coefficient is 1, P is a constant, Q is constant. So P comma Q are constants, but R is a constant or a function of X only, or a function of X only. Here X is nothing but independent variable. So whenever this happens, then this is called a second order linear equation with a constant coefficient. This is 1, this is constant, this is constant. All coefficients on the LHS are constants. Right hand you can have either a constant or a function of X only. Now I need to get the general solution of this equation. See, one simple way is, as usual, you know how to find YC value and how to find YP. But in this case, we were going for different particular integrals. Let us see. When you consider this in D form, this will be in the form D square plus PD plus Q of Y equal to R. So what is my auxiliary equation? Auxiliary equation is M square plus PM plus Q equal to 0. So therefore, it is a second degree equation. We will get exactly two roots. Exactly two roots. So based on the nature of these two roots, I can get YC value. So YC, I call it as C1 into U of X plus C2 into V of X. This is very useful to get the whole total general solution. So it's a second order equation. When you solve this, you get two roots. So assume that YC equal to C1 into U of X plus C2 into V of X. I don't know what is U, what is V, unless or until I know this, this equation. So if I don't know this equation, I can say that YC will be like this. If you supply the values of P, Q, I can easily say what is YC. But if you don't know what is P, but as far as our knowledge is concerned, here P is a constant, Q is constant. So in the regular way, you can easily find YC value, that is C1 into U of X plus C2 into V of X. Now this U of X and this V of X help us to get the value of YP. Now let us see, here let YP equal to A into U of X plus B into V of X. This A into U of X plus B into V of X. This U of X and V of X directly we are taking in YP. In the previous cases, YP is completely independent on YC. But in this case, in case of variation of parameters, YP depends on YC because we are taking U of X and V of X from YC. Therefore, YP will be A into U of X plus B into V of X. Now, let me discuss what is this A and this B. This A is nothing but minus integral V into R divided by Wronskian of U comma V dx. And this constant B equal to integral U into R divided by Wronskian of U comma V dx. Therefore, what is this U? This U and this V, they are part of YC. Therefore, you need to find Wronskian of U comma V and write this in place of denominator. And this R is nothing but this R, U is this and V is this value. Therefore, by finding A value, B value, you can substitute here, you will get the value of YP. Therefore, once you get YP value, the general solution is given by Y equal to YC plus YP. So, in this manner, you can handle any second order linear differential equation with a constant coefficients. So, variation of parameter is very, very useful in finding particular integrals of very complicated functions like tan, cot, cosecant, secant, etc. But drawback is it is restricted only to second order equations, right? Note these points. Consider a second order linear equation with a constant coefficients. Consider a second order linear equation with a constant coefficients of the form d square y by dx square plus p dy by dx plus qy equal to r. D square y by dx square plus p dy by dx plus qy equal to r. Equation 1. Where p comma q are either constants, where p comma q are either constants or p comma q are constants, p comma q are constants, and r is a constant or a function of x only. P comma q are constants, they are fixed. or is a constant or a function of x only, or is a function of x only, right? Now work out these entire points. Parameters. First problem, solve d square y by dx square plus y equal to secant x. Let us solve this equation. D square y by dx square plus y equal to secant x. In capital D form, this is d square plus 1 of y equal to secant x. Now let us find yc at first. The auxiliary equation is m square plus 1 equal to 0. So therefore m equal to plus or minus I, complex roots. So therefore m equal to 0 plus or minus I. Now basically this is alpha value and beta value is 1. So roots are complex roots. Alpha is 0, beta is 1. Therefore my yc equal to e power 0x, e power alpha x into c1 cos beta x plus c2 sin beta x, but beta is 1. So therefore c1 cos x plus c2 sin x. Therefore yc equal to c1 into cos x plus c2 into sin x. So here u of x is u of x, cos x is u of x, and sin x is v of x. U of x is cos x, v of x is sin x. These two things I use in yp. So therefore in this case yp equal to a into u of x plus b into v of x. So this is a times u of x is cos x, b times v of x means sin x. Now let us find what is a and what is b. So here a equal to minus integral v into r divided by Wronskian of u comma v dx. Now what is the Wronskian of cos x comma sin x? We know that Wronskian of cos ax comma sin ax equal to a. Here a value is 1. Therefore Wronskian of cos x comma sin x is 1. Therefore a value is minus integral v is nothing but sin x, r is nothing but secant x divided by 1 dx. So therefore this is a equal to into my integral minus sin x divided by secant x. I can write it as cos x, 1 by cos x. So cos x derivative is minus sin x. So it is in the form integral f dash of x divided by f of x. Cos x derivative is minus sin x. Therefore this is nothing but log of denominator. So log cos x. Next I find b value. This is integral u into r divided by Wronskian of u comma v dx. So what is u? U is cos x. R is secant x. Wronskian is 1. Cos into secant is 1. So integral 1 dx. Therefore x. Therefore what is my yp? A into cos x, but a is this. So therefore this is the log of cos x into cos x plus, so b is x, x into sin x. This is yp value. Therefore the general solution is y equal to yc plus yp. This is my general solution. So this is yc value and yp equal to this log of cos x into cos x plus x sin x. Only thing is you need to go for normal, very normal integral, simple calculation. So the important point is use the values of u of x and v of x which we got through yc in yp, so that you can find Wronskian very easily and hence you will get the particular integrals. Don't think that here this variation of parameters is applicable only for trigonometric functions. Even you can use 6 functions what we have seen, that is exponential functions, sine function, e power ax into v, polynomial expression. There also you can apply these. Directly you can apply this. Okay. So note all these points. I think this is clear. Next, we solve one more question on variation of parameters. I am not changing LHS part. Just I will do some changes in RHS part. This is, for example, cot x. So d square y by dx square plus y equal to cot x. So therefore here RHS is cot x. So no change in YC value because I did not change on LHS side. So no changes in YC. C1 cos x plus C2 sin x. So only thing is because of this changes, I will get different values of A and B. So here Wronskian is again same. Now let us try to find A value. Here A value is this. Therefore A equal to minus V. V is nothing but sin x. This R is nothing but cot x. Divided by Wronskian is 1. So therefore this is minus sin x into cot x is cos by sin x. Therefore this will be cancelled. So what is integral cos x sin x? Therefore A equal to minus sin x. Integral cos is sin. Already we have minus symbol. So A is minus sin. Now B equal to integral u into R by Wronskian. U is cos x. But R equal to cot x. Therefore this value is B equal to integral cot x into cos x into cot x. This cot x I can write it as cos x by sin. So this is cos square x by sin x dx. Therefore this cos square x we can write it as 1 minus sin square x divided by sin x dx. So this is integral 1 by sin. 1 by sin is cosecant x dx minus integral sin x dx. Therefore this is integral cosecant x is log of cosecant x minus cot x minus integral sin is minus cos x. Already we have minus symbol. So this is cos x. Therefore this is the value of B. So we got A value equal to minus sin x and B equal to slightly complicated log of cosecant x minus cot x plus cos x. But this is the only procedure to find particular integrals of complicated expressions, right? So, but the drawback of this is it is restricted to only second order equations. So this is A, this is B. So replace A value here, B value here. Finally, the general solution will be y equal to yc plus yp. And we already got yc value, this is, and yp equal to A value is this and B value equal to this. Note down these points. Now with this we have finished all concepts in ordinary differential equations. Now let us start classroom workbook from question number 53. Just all of you go through classroom workbook. Let us start from question number 53. They asked general solution of a second order differential equation, but it is a Cauchy's linear differential equation. Just go through the question, you can understand easily. The equation is x square into d square y by dx square, x square into d square y by dx square minus x dy by dx plus y equal to 0. We need to find the general solution of this equation. See, right side is 0, so we need not find particular integral. Its general solution will be y equal to yc only. Now, in this case, this equation can be written like this: x square d square minus xd plus 1 of y equal to 0. Now, here powers of x and powers of d are same. 2, 2, here powers are 1. So, it is a Cauchy's linear equation. Cauchy's linear equation of second order. Now let us handle this. In order to get the general solution of this equation, what we take is x equal to e power z. Then in that case, what will be changes? xd equal to theta, x square d square will be equal to theta into theta minus 1. What is this theta? This theta is nothing but differential operator with respect to z. So we were following the procedure to solve Cauchy's equations. X equal to e power z. xd becomes theta. X square d square becomes theta into theta minus 1. Now let us substitute these values in this equation. So this becomes x square d square is theta into theta minus 1. That is theta square minus theta plus 1 of y equal to 0. So this implies theta square minus 2t theta plus 1 of y equal to 0. So this is an equation with the constant coefficients. Therefore, this auxiliary equation is, m square minus 2m plus 1 equal to 0. So this implies m minus 1 whole square equal to 0. So roots are 1, 1, real and equal. Roots are real and equal. When you have real and equal roots, the value of y equal to c1 plus c2. Don't write x because x is converted to new variable z. So therefore c1 plus c2 z into roots are 1, 1. This is e power 1 z. Therefore y equal to c1 into e power z plus c2 into e power z into z. This is my general solution. But finally, this z is replaced by log x. So here e power z is x. Therefore this is c1 into x plus c2 into x into this z is nothing but log x. Therefore this is the general solution. So therefore it is constant into x plus constant into x log x. So it is constant into x plus constant into x log x. So option D is written. So in place of C1 and C2, they mentioned capital A and capital B. They are general constants. Therefore option D is right answer. Next, let us discuss question number 54. Consider an equation x square d square plus xd minus 4 of y equal to 0. This is the equation given with the boundary conditions y of 0 equal to 0 and y of 1 equal to 1. The complete solution of this equation is, options are given. How to handle questions like this? It's a second order equation. Two boundary conditions are given. Directly particular solutions are given in options. So let us try to verify boundary conditions. If only one option satisfies both the boundary conditions, that could be right answer, right? Even if you don't get right answer by verifying options, at least we can eliminate one or two options. That will happen in this case also. Let us see. What is option A? It is x square. Now here all these are y values. When you replace x by 0, y value is 0. When you replace x by 1, the value is 1. So it satisfies both boundary conditions. So do not confirm and don't eliminate. Hold this option. Come to option B. It is sine of pi x by 2. Here also, when you replace x by 0, sine 0 is 0. Replace x by 1, sine 90 is 1. So even second option also satisfies both boundary conditions. So hold this. Option C. This is e power x into sine of pi x by 2. Now replace x by 0, e power 0 into sine 0, 0. So it satisfies the first boundary condition. So let us verify second boundary condition. E power 1 into sine 90, that is e power 1. So when you replace x by 1, it does not fulfill the second boundary condition. So it fails second boundary condition, so eliminate this option. Option D. This is e power minus x into sine of pi x divided by 2. Now here also when you replace x by 1, second boundary condition, you will get e power minus 1. But e power minus 1 is not 1. Therefore, this is a wrong option. Therefore, when you look at this, the second boundary condition is not valid for last two options. The second boundary condition fails in last two options. Therefore, you can eliminate options C and D. So, answer can be either A or B. You can easily say, if the roots of this equation are complex roots, then you will get sine function. Otherwise, it will be x square only, right? Now, let us see. It is a Cauchy's linear equation. So, in order to solve this equation, I will take x equal to e power z. So, therefore, xd becomes theta, x square d square equal to theta into theta minus 1. So, this is nothing but theta square minus theta. Now, substitute here, we get theta square minus theta plus theta minus 4 of y equal to 0. So, this implies theta square minus 4 of y equal to 0. So, my auxiliary equation is m square minus 4 is 0. So, one root is plus 2, another root is minus 2. So, here roots are real roots. So, when roots are real roots, you won't get this sine function. So, therefore, answer is A. Just simply we can say, by using second boundary condition, last two options are eliminated. So, answer can be either polynomial function or sine function. But when I gone through finding the roots of auxiliary equation, I got real roots, not complex. When I don't get complex roots, how can I expect sine function in the general solution? Therefore, option B also wrong answer, A is right answer. So, therefore, here I have real roots. There is no chance to get this. So, option A is right answer. So, this is one way. So, directly we are getting x square. If you ask me to get the general solution completely, how to get this? So, here I have 2 and minus 2. Therefore, in this case, y equal to c1 into e power 2z plus c2 into e power minus 2z. Therefore, y equal to c1 into replace e power z by again x. So, this is c1 x square plus c2 by x square. The difficulty at this moment is when you are finding c1 and c2, there are some issues. What are the issues? The first boundary condition creates some problem. Y of 0 is 0 because x is written in the denominator part. So, in that case, you will get infinity form c2 by 0. So, to avoid this difficulty, multiply this equation with x square. So, x square y equal to c1 x power 4 plus c2. Now, let us apply this boundary condition. When x is 0, y is 0. So, 0 equal to c1, this is 0 plus c2. Therefore, c2 equal to 0. Substitute c2 value here. I get y equal to c1 into x square. Apply the second boundary condition. So, y value 1 when x is 1. So, c1 equal to 1. So, replace c1 here. So, y equal to x square. Therefore, this is my final complete solution. Y equal to x square. Option A. Okay. This is for your reference only. But during writing gate examination or any competitive examination, when options are given, don't do entire calculation. It's a simply wastage of time. Got it? So when you are handling questions like this, always follow one simple technique. Particularly in case of differential equations, my suggestion to all of you is when particular solutions are given, try to verify boundary conditions. If only one option satisfies all boundary conditions, that could be right answer. But sometimes what will happen is all options will satisfy all boundary conditions. In that case, try to work out this and compare options with your general solution. At least by doing 50%, you can get the answer. So like in this case, it is happened. See, in this case, roots are real roots. When roots are real, you don't get sine function. But unfortunately, here we have a sine function. Therefore, you can eliminate this. So these two options are eliminated by using second boundary condition. Therefore, option A is true. Even we got it directly by finding general solution and applying boundary conditions to get C1 and C2. Okay. Note these points. Next, let us go through question number 55. Question number 55. 1 by xd plus 1 of x inverse is, options are given. 1 by xd plus 1 of x inverse is given. We need to find the correct option. We need to find the correct option. Now you can see this is basically in the form 1 by f of d of, here f of d means f of xd, function in xd. 1 by f of xd of q of x. So basically this is what? This is particular integral of Cauchy's equations. This is particular integral of Cauchy's equation. So if you want to handle Cauchy's equation, then what we need to do is we need to take x equal to e power z. Therefore this expression becomes, xd becomes theta. 1 by theta plus 1 of, this is e power minus z. Therefore this is, now here a value is minus 1. Coefficient of z is minus 1. This is theta. Let us try to apply case 1 of particular integral. What is case 1? 1 by f of d of e power ax. Here what is coefficient of z? Minus 1. So when you replace theta by minus 1, see when we are working with variable x, that is 1 by f of d of q of x, that is e power ax. Then we try to replace d by small a if the denominator is not 0. That means I am going to apply case 1 of particular integral. But in this case a is coefficient of z, that is minus 1. When you replace theta by minus 1, it will be 0. Therefore this minus a is a root of this equation with multiplicity 1. Therefore this is replaced by z power 1 by 1 factorial into, we don't have any term to replace theta by minus 1, further this. Therefore z power 1 by 1 factorial into e power minus z. Therefore this expression is z divided by e power z. But what is z? Log x. What is e power z? This is x. Therefore option B is a right option. Log x divided by x. What we have done is, this is nothing but particular integral of Cauchy's equation, because it is a function in single variable xd. I feel that xd is a single variable. 1 by f of xd of q of x. So it is nothing but particular integral of Cauchy's equation. How to handle this? Take x equal to e power z. Then xd becomes theta and this x becomes e power z. So it is 1 by theta plus 1 of e power minus z. Now here the coefficient of z is minus 1. So when you replace theta by minus 1, the denominator gets 0. That is, minus 1 is a root of this equation with multiplicity 1. Therefore I am going to apply case 2 of particular integral. So at this moment I am going to apply case 2 of particular integral. Case 2 of particular integral. Therefore this is nothing but z power 1 by 1 factorial, because it is a root repeated one time. So z power 1 by 1 factorial into e power minus z. This is z by e power z. Hence it is log x by x. So option B is right. Now let us discuss question number 56. It is 1 by 4x square d square plus 8x d plus 1 of ln x, where d equal to d by dx. So we need to find out the particular integral of Cauchy's equation, same as previous model, but we don't have any clarity in this case, which case we need to apply, unless or until if I go for some further steps, then we get some clarification. Let us see. So in order to get this, take x equal to e power z. Then this expression becomes 1 divided by 4 into x square d square becomes theta square minus theta plus 8 theta plus 1 of, when x is e power z, log x becomes z. Z means z power 1. So this is nothing but 1 divided by 4 theta square minus 4 theta plus 8 theta plus 1 of z power 1. So therefore this expression is nothing but 4 theta square plus 4 theta plus 1 of z power 1. Now this is nothing but 1 by f of d of polynomial expression. Previously we have polynomial expressions in the variable x, but there is no more x because x is converted to z. So this is a polynomial expression. When you are handling particular integrals of polynomial expressions, we need to take least degree term of f of theta as common. Here not f of d, f of theta, because d is converted to theta. So here 1 is the least degree term, so you need not take 1 common. This expression is nothing but 1 by, this denominator is 1 plus 2 theta whole square of z power 1. Therefore this is 1 plus 2 theta whole power minus 2 of z power 1. Now you can see this is in the form 1 plus x whole power minus 2, but here power is 1, so I can write like this. This is, for example, x, but don't confuse this x with this, it is some different. So 1 plus x whole power minus 2x is 1 minus 2x. I don't write plus 3x square, because when you write theta square of z power 1 is constant only, 0. Therefore I will write the terms up to this. So 1 minus 2x of z power 1. So here what is x? 2 theta. So this is 1 minus 4 theta of z. But what is theta? D by dz. So d is a differential operator with respect to x. Theta is a differential operator with respect to z. So z minus 4 into d by dz of z. This is 1. So therefore this is z minus 4. But when x is e power z, this x is z is log x. So ln of x minus 4. So therefore the result is ln of x minus 4. Only thing is you try to concentrate this point. So when you are handling particular integrals of polynomial expressions, we need to go for suitable series expansions. So we got 1 plus x whole power minus 2 and we got this result. So the result is log x minus 4. Hence it is option number B. So option B is right answer. Next, let us move to question number 57. This is particular integral of Cauchy's equation. They were asking particular integral. So yp equal to 1 by x square plus x square d square plus 2xd plus 1 by 4 of q of x is 1 by square root of x. So we need to find yp like this. Now this is Cauchy's equation, x equal to e power z. Therefore this expression becomes 1 divided by, this is theta square minus theta plus 2 theta plus 1 by 4 of, when x is e power z, this becomes e power minus z divided by 2. So this denominator is theta plus 1 by 2 whole square of e power minus z by 2. Therefore, this expression will be equivalent to here what is a value? Minus 1 by 2. When theta is replaced by minus 1 by 2, it will be 0. Therefore, this minus 1 by 2 is a root of this equation with a multiplicity 2. Therefore, at this moment, try to apply case 2 of particular integral. Therefore, this is replaced by z square by 2 factorial into e power minus z by 2. So, therefore, yp equal to z square by 2 factorial into e power minus z by 2. But what is z? Z equal to log x. So, this is log x whole square by 2 into, but e power minus z by 2 is root x. Therefore, the answer is log x whole square divided by 2 root x. So, therefore, this is option C. C is right answer. So, we have applied case 2 of particular integral. Note these points. This is the end of session. In the next session, we discuss one classroom workbook question on Wronskian, followed by the concept partial differential equations. Thank you so much.